So we will be building a 9-volt continuity tester. As you can see, I've already tinned, cleaned, preheated my soldering iron. I'm using SN100C lead-free alloy with an NC601 flux, 0.032 inch diameter solder. Now, if we look at the schematic of what we are building, and I very precariously set down my soldering iron, it is a 9-volt battery, a 1 kilo ohm resistor, a red LED, and then 2 contacts, which we will be using for testing the actual thing that we are poking with the continuity tester. Now, if this were a more complicated circuit, we would breadboard it, but that is not necessary here. So, take our LED, which is packaged with this strange masking tape stuff that I can never really get to come off cleanly without rubbing alcohol or acetone, but in this case, we do not need the whole length of the leads. Also, these are discount surplus LEDs, so they have these little cross pieces here which keep it from sitting flush with the board. That is not a standard feature of LEDs. Now, we can take that, put it into our perf board, and then, right, so you put the LED into the perf board. I have clipped the little parts that were sticking out in an attempt to make it sit flush. I don't know if I have succeeded. It'll depend on... Nope, looks like it will not. This is going to be a very beginner-looking project, as you can see, no doubt. However, it's a good starting point. Once you put the part into the board, you bend the leads on the opposite side so that it stays sitting flush. This means that you can then solder it in place. Let me see if I can get a good view of this process as it is occurring. So, this is perf board, copper clad, with the part stuck through it. Take your soldering iron, clean it off, put a little bit of extra solder onto it, then tap that bit off into some sort of container. Then bring the soldering iron so that it is in contact with both the little copper donut on the bottom and the lead you're trying to solder. Then apply solder from the other side. This is what you want the joint to look like. It'll smoothly reflow and make sort of a concave cone shape. Do the same for the other lead. It's best to apply the solder from the opposite side of the iron to make sure that it's actually the joint that is melting it. If you do not do this, as I did not do for the second one, you get this issue where the solder doesn't actually flow all the way around the entire joint like it's supposed to. Worst case, you can get what's called a cold solder joint, which is where it looks like it's soldered, but it's not actually electrically connected because there's a tiny gap in there from oxides on the surface, contaminants, what have you. And those are really hard to troubleshoot. But you want it to look something like this. And then here's our beautiful LED. Another fun pro tip is that you don't need, if you want this LED to be viewable from all directions, don't leave a lens on it. This lens, its purpose is to focus the LED's output of light into a narrow beam coming off of it. So you can correct this either by buying wide angle LEDs, which are more expensive, or by cutting off the top of the lens, being careful not to cut off. There's an internal bond wire that you can see barely. Anyway, there you go. Now it's a wide angle LED, like magic. I don't think I cut the wire, but we will see. Now, this is the LED part of the schematic. Let's see what we've got. We need battery, a switch, and the LED, and then a resistor. It looks like I have the resistor connected to the negative lead of the LED, which, as you will remember, has a flat on the case, is usually connected to the larger metal piece inside the case. And so that means this side is the negative terminal. So now we can attach our resistor. The nice thing about resistors is it doesn't matter which way you put them, unlike light-emitting diodes. So it can go just somewhere on the board. All right, there it is. Now it's at a place. And so we can press it down, bend its leads in order to hold it in position, and then you could solder the lead first, but in this case it's going to look nicer if I bend the lead over. So now I'm making a connection here. So I'm going to be connecting the LED and the resistor using solder, as one does. What else would you use? I'm going to have to figure out how to get this set up so that you can get nice high-resolution pictures and video of all of this, dear viewer. But this will have to do for now. So this glob here is the connection between the LED and the resistor. So there is excess wire that we no longer need. And so now you can see our circuit is beginning to take form. Now, this is going to go to a lead for testing. For testing things that are conductive, I'm going to be using this pin. I bet I can get away with just soldering it to the board. I think. Let's find out. Let's see if I can solder to this pin. I have not tried soldering to these before. It is kind of hit or miss whether you can solder to a particular metal. There is a long and complicated metallurgical explanation, but we do not need to get into that here. So far, so good. Now, my first impulse is to touch it, which will badly burn me. So I'm not going to do that. I have to wait a little bit for it to cool down. So this is now soldered. And then I'm going to solder this to a pad, and then the other end of this wire to one of these pads, which will help keep the pin fixed in position. Okay, so now this is fixed in position. And we can work on the rest of the schematic. So back to that schematic. We have a 9-volt battery, a switch, a red LED, and then a resistor, and 2 output pins, one of which has already been attached, the other one has not. So I'm going to start from the battery connector now. Remember, red is positive, black is negative. For these videos, I'm going to use conventional current, which is saying that it comes out of the positive lead and goes into the negative lead. This is not strictly true. Electrons flow from negative to positive, and if you have a solution of, say, salt water, then the positive ions in it will flow from plus to minus, and the negative ions will flow from minus to plus. And if you have pure ice, then conduction can be moderated by protons, which get swapped from hydrogen atom to hydrogen atom, going from plus to minus. Anyway, if you say it goes from plus to minus, which is called conventional current, then the arrows on your little symbols, like this LED, are pointed in the right direction, and so it's easier to keep track of in your head. Now, we'll need some wire strippers. And then to strip these 2 wires, I like how I'm doing this all over a hot soldering iron, as is tradition. So it's now I have stripped the wires. I have this going directly to the switch, this Nintendo Switch, which was not as well received as a Christmas present as I hoped it would be, but that is neither here nor there. So now these wires have gotten kind of old and sad, so it is best to strip fresh wire, as it'll be easier to work with. I'm going to call this 16 gauge. Maybe it's 18. So this is now exposed stranded wire. And then the positive connection is going to go to one terminal of the switch, as we can see from our lovely schematic here. And there are various ways to do this, but the easiest way to start is by tinning this terminal, then tinning the wire, then melting them together, at least in my experience. I'm sure someone will weigh in and say there is some reason that this is the wrong way to do it, but as long as it works, and also this is like very much an introductory project, and yeah, yep, that's what we do here. Okay, so now you can see that there is a glob of solder on the switch now where there was not before, and if the solder is sticking to something, it'll form a low angle with it. If you've got a sphere on top of your surface, it means your solder probably isn't stuck. Once it's cooled, you can see if you can peel it off with a fingernail. If you can, it's not adhered properly. If you can't, it probably is. And how do you test beyond that? Well, you need a continuity tester, which is what we are making in this moment right here. So I have tinned these wires, And now, according to the schematic, the positive output of the battery is going to go into one terminal of the switch. It doesn't matter which terminal you connect it to. Switches, like resistors, you can connect them either way, especially a single pole, single throw switch. It's either connected or not. There's not much more to it than that. So now we have our positive terminal from the battery going to the switch. Then this will go into the positive lead of the LED here on our circuit board. This is not going to be winning any design awards for beauty or elegance, but this isn't for that. It's so that you can learn how to do these things and hopefully apply them to your own life, make the world a better place, etc., etc. So I'm going to tin both of these wires, then bring them together once they are fully tinned. The reason you want to melt the solder on the thing that's being soldered instead of on the iron tip is because when you melt the solder, the flux comes out and it spreads over the surface and cleans off any oxides that would prevent it from adhering to them. Now, once this reflows, I'm going to connect it and then hold it and then let it solidify. All right, so now this is connected. And then the last thing we need is another pin so that we can use the continuity tester. Also, note, let me see if I can get a good picture of this. My soldering iron is starting to become clogged. And it has turned, let's see, can I get more light on this? Is there any way I can improve this? So one part is shiny and silvery, and the other part has turned black, which means you can no longer melt solder on it when it is black like this. It's just like rubbing it on it. So this is the point where you want to use the tip cleaning sponge. This is brass wool, I think, to clean the oxide that's built up on the tip, and then you want a fresh, shiny layer of new solder on it. See how it flows all the way around the tip. Then you tap off this excess ball of solder, and then you end up with something like this. Adding a little bit more solder applies the flux, which makes it pull back into a spherical shape because it eats away the oxides that have built up on the surface of the solder. So now we will be attaching this hat pin, dissection pin, some flavor of pin. It's going to be one of our output connections. So I can solder to this. You can't solder to aluminum for reasons that I will get into later. Basically, the aluminum metal is always forming an oxide on its surface. Pure aluminum metal reacts very quickly with the oxygen in the air, and it forms a clear oxide layer of aluminum oxide, which is nice in one sense because it makes sure that your aluminum stays shiny and has a clear protective layer that grows on it, but that layer is non-conductive. So you'll have issues with getting reliable connections to aluminum. You can't solder on it because that conductive layer prevents the solder from adhering. Now you can blob mineral oil on it, then use sandpaper while keeping the mineral oil on it, and then solder through that, but it's not generally done. So now we can connect a battery, and then we have our power switch. Turn it on, and then this is our continuity tester. Whenever these things are in electrical contact, this light will light. So you can tell with it, which sorts of things are conductive and non-conductive. Paper does not conduct. This fountain pen won't conduct very well on the anodized layer because that's non-conductive, but on the clip it conducts. On the areas where the anodized layer has worn off, it conducts, but the layer itself is non-conductive. And another thing which is conductive, if I have not lost it, is this carbon rod. This is salvaged from the inside of a standard heavy-duty battery, which means Leclanché carbon zinc battery. They all come with a free carbon rod. Wow, look how conductive it is. So, what makes something conductive? Like, how do you tell? It has to do with whether or not there are any movable charge carriers in it. So, and what do I mean by that? Usually electrons, not necessarily. So metals always have 2 electrons in their very outermost shell. Most metals. We'll get into the chemistry in more detail later. Most metals have 2 free electrons in their outer valence shell, and all of the atoms are just sharing them in a giant pool that swirls around. So if you apply an external voltage like this, you can push those electrons around and they'll flow. Salt water has free ions in it. For regular table salt, sodium chloride, you get sodium ions and chlorine ions. And the sodium ions are positively charged, the chlorine are negatively charged. So when you apply a voltage, you can push those ions around and a current will flow. Basically, if something has free electrons or free charge carriers of any kind, it will conduct. So if you wanted to make vacuum conductive, you could take a filament and heat the filament so it jostles and shakes off a cloud of electrons that just sort of hang out around it, and you can move that cloud of electrons around. That, for example, is how a vacuum tube works in the most basic description. But so now we've built our first piece of equipment which can tell you whether or not 2 wires are connected or not. Or whether a material is conductive. So if you had an unknown cable that didn't have a chip in it, because this thing is outputting 9 volts, and most chips, well, most, in which environment? Many chips can only handle 5 volts. As time goes on, it seems like the trend is for voltage to become lower for operating electronics. So it's gone 5 volts, then 3.3 volts, then 2.5 volts. Then we're down to like 1.8 or 1.2, I think. But that is all case-by-case basis. If you had a cable that had no chips in it and you wanted to see what one lead on one side of the cable went to the other one, you could use this to poke to see if they were connected. Till next time.